Yeah, excited to be here. Excited to talk. I've got not that many slides, so we'll see. I'll try to slow down, take it slow. Some of the objectives here. I really just want to provide a top level view of this gravitomagnetism. Frame dragging is another name for it. We'll talk about some of the experimental anomalies surrounding that might be related to this effect, propose potentially some next steps for an experiment. And my idea here is really to stimulate discussion, figure out, is this idea worth pursuing? I'm looking for honest feedback. And so I don't think this is going to take the full hour. I'm hoping maybe 30 minutes, maybe 40 minutes, and maybe we'll save the rest for some open discussion and you guys can give me some honest feedback. An outline of the talk. I'll start with an about me and just kind of how I got into this topic and what my career is in, sort of the perspective that I'm coming to the table with. I'll talk about motivation, which I think is probably the same for many people that are in this community, UFOs. We'll talk about obviously gravitomagnetism, the evidence, potential implications, and then sort of the fundamental theory that I'm getting at, which is not new. Most of this stuff is not new, but perhaps I'm putting a new perspective on it, coming from a microwave engineering background, and some of the relevant experimental anomalies that might be hinting at the fundamental phenomenon. And then we'll have some discussion. All right, so about me, EM Drive at Cal Poly. So I studied aerospace engineering at Cal Poly SLO from 2012 to 2016. And I was studying rocket science and I got pretty fed up with it, because you're not going to get to other star systems with rockets. I think that's pretty obvious. So NASA at the time, NASA EagleWorks was testing this asymmetric resonant cavity. And if you're not familiar, it's this frustum-shaped, I don't know if you can see my cursor, but you've got this frustum-shaped or conical-shaped copper cavity where you're putting microwaves in, they're resonating, and the idea was that you're pushing off the fabric of space-time or perhaps emitting some sort of quantum vacuum plasma. Harold White and a couple others where Paul March were working on this. And, they're getting results and they couldn't explain them. And so as an undergrad, I got really interested in the topic. I participated a lot in the NASA Space Forum, which I know a lot of the people in this community also were around there at that time and maybe still are today. So I taught myself how to do, electromagnetic simulations using EM Pro, sort of a free software for students. I took apart a lot of microwave oven magnetrons and I took out one of the antennas, basically made a homemade magnetron antenna. We brazed a little SMA port to a magnetron antenna and we're able to hook that up to a VNA, to a vector network analyzer, to basically measure the resonance of this tunable cylindrical cavity. So you see in the middle here, we've got this cylindrical resonant cavity. We made it asymmetric by using like a dielectric loading. So instead of having the shape be a conical shape, which is really hard to tune, we made a cylindrical shape and we're able to tune that using a plunger, basically. And this is funded by the university. We got a small grant to do this, me and another student, a friend of mine, and able to borrow a lot of equipment from the university. And we used a laser position sensing detector to basically reflect off of a mirror. And all in all, it came out to a thrust stand that could detect about 2 millinewtons reliably. You can see on the oscilloscope here, we've got that green kind of oscillation is actually just noise on the order of, I think, less than a millinewton or so. And so, yeah, so we could reliably detect about 2 millinewtons. And, but, I spoiled the surprise here. The experimental outcome, thermal expansion of the leads was the problem. We don't have an onboard power supply. We're plugging this in externally. We thought this pendulum, maybe we could orient the wires so that we don't have that issue. But basically, every time we fired it up, whether it was on resonance, whether it was off resonance, didn't actually have the effect that we were going for. We couldn't isolate the effect that we wanted to see. So could not see the anomalous thrust, but that turned me from a microwave engineer or an aerospace engineer into a microwave engineer. So that led to my first career move, which was doing microwave plasma reactors. So this is kind of just a new technology to basically convert natural gas, methane, into carbon and hydrogen, which has a lot of applications. You can make different types of carbons. You can make the carbon more graphitic. You can make the carbon more like graphene. Right now, we actually have a pilot that's deployed in Pittsburgh, Pennsylvania, and we're working to scale the technology and deploy it in other applications. And so that's all of this to say is, this is my kind of real career. This is where I'm coming from when I present this gravitomagnetism stuff. I also had a few years working at General Atomics doing nuclear fusion. Got to visit ITER in 2022, which is pretty amazing. The scale of that place is mind-boggling. But at General Atomics, I got very experienced with COMSOL multiphysics, which I'll talk about a little bit more later, and designed a lot of new electron cyclotron heating equipment, which is basically really high power microwaves at really high frequency. And while I was at General Atomics, they had an open pitch fest. So they invited anybody to come out with their wild ideas, and they said that they would fund somebody. And so I worked really hard to put together a pitch for what I thought would be the best theory for anti-gravity or space-time engineering. And so that's kind of where this presentation sort of was born. And I've done a little bit of refinement to present to you today. But yeah, I did. I got runner-up in the competition, did not win, unfortunately. I think they thought it was a little bit too out there, even though that's what they wanted. But that's how it goes. So motivation, unidentified aerial phenomenon. I think that we're all on the same page here. This is straight from the DIA report, Director of National or DNI report, that basically says, these things have appeared to demonstrate advanced technology. They move at considerable speed without discernible means of propulsion. No thermal signature on these IR videos. These things are moving. We've got pilot witnesses talking about craft moving at 90-degree angles, pulling massive amounts of G's, accelerating instantaneously. All of these are consistent, excuse me, with space-time engineering, i.e. gravity field modification. So some sort of space-time warping is going on. I think there's ample evidence that this is a real thing. The question is, how do you do it? And so that's been my real, hobby, passion for a long time. And yeah, so let's talk about sort of the theory about how that could work. So it kind of comes back to frame dragging, which is the same thing as gravitomagnetism. So this goes back to Einstein's time. Lenz and Thirring derived frame dragging from general relativity. And it took us until about 2004 to actually measure this with a high degree of certainty. And so, I think it was Gravity Probe B and a couple other satellites, as well as now we've got quasar measurements that are measuring this effect. And basically what this says is that the curvature of space-time depends on mass and velocity components. So it's not just your static rest mass, it's also the movement of that mass relative to other mass. So the angular momentum vector creates a warping of space-time that is similar to the magnetic field created when an electric charge moves through space. Some of the differences is you get a negative sign. So instead of like charges attracting each other, instead of like charges repelling each other like you do in, when you have two electrons, you've got like charges attracting each other, and that charge is now mass. And obviously we've got this gravitomagnetic field, which is orders of magnitude smaller than G. And so that's the big challenge here is, okay, so we've measured this effect. The problem is it's tiny. That's why it took us so long to actually reliably measure it. And if that's the case, how could we possibly use this to do anything useful? Oh, wow, some things got blown out of proportion here. All right, so on the left here, we've got electromagnetism, which everybody should be familiar with, Maxwell's equations. You've got your Lorentz force. So when you've got current moving through a wire, it creates a magnetic field according to the right-hand rule. And you've got an electromagnetic impedance of free space. So when you design an antenna, it needs to be able to radiate properly to its environment. And so the analogy suggests that gravitation acts in the same way. You've got gravito-electromagnetism is basically saying that your gravito-electric field is just like your Newtonian gravity, and your gravitomagnetic field is your weak component of gravity. And it's not the same force as a magnetic field. It is just an analogous analogy. So within the analogy, you should have a gravitomagnetic Lorentz force. You should have a gravitomagnetic pointing vector. you should have gravitomagnetic impedance of free space. And I'll come back to that in a bit. But basically, this gravitomagnetic field comes from angular momentum. So, at every scale, if anything has angular momentum, it is going to create a gravitomagnetic field. And this is actually according to the left-hand rule, which I find kind of intuitively satisfying that this would be the relationship between, mass, sort of interpreting it as a charge and looking at it with respect to electromagnetism. But of course, I'm going to say that as the microwave engineer. It seems very it seems like a nice way to formulate everything. Okay, so I talked in the intro. I did mention that I wanted to look at astronomical implications or cosmological implications, but in doing some more research in preparation for this talk, I was actually a little bit stumped. There are a few papers out there that suggest, like this one from Ludwig, who says that, hey, if we include gravitomagnetic equations in our galactic rotation calculations, we can potentially explain some of these dark matter observations. So instead of this anomalous galactic rotation being responsible or being caused by dark matter, this invisible stuff that we can't measure that's distributed very specifically throughout most galaxies, but not all, maybe that is actually the movement of the galaxy itself that is pulling the galaxy together. And we don't need any dark matter, sort of correction factor to include. But then I dug into a little bit further and I found examples that refute this idea, like NGC 1277 is a relic galaxy in the Perseus cluster. It's dark matter deficient, much less than you would expect, and compared to most galaxies, but it's also a very fast rotator. So that kind of threw a wrench into this idea. And I'd say maybe there's something there. And I'm not a cosmologist, I'm not an astrophysicist. So, this is just me reading a bunch of scientific papers trying to figure out what's going on. And my conclusion here is there is no conclusion to be made yet. So gravitomagnetic interpretation might be a partial explanation for dark matter, or it probably does affect galactic rotation. It probably does affect the movement of stars, but I think that saying that dark matter is fully explained by this is probably a bit presumptuous. So I think there's interesting research to be done here, and I hope that more people look into this because I think that there's probably something there that we're missing. So then it comes down to what about at the quantum level? So if we say that the gravitational field can be affected by gravitomagnetic induction, so if we can change an angular momentum, then we can create a gravitational field. Well, why don't we look at the quantum level? A material, if you think about it, has intrinsic angular momentum in the form of quantum spin. Every atom in any given material has a quantum spin number, unless that spin number is zero. Or not. I feel like it could be wrong here. That might not actually be zero. But anyway, it's different atoms and different isotopes have different spin numbers that are sort of ground state. And so really the idea is that not all vectors within a material are aligned. And if they are, they're not changing in time. And so if you could align all of the atomic angular momentum vectors within a lattice across an entire material, and you could drive a time rate of spin or time rate of change of that atomic spin number, and then you could also consider the macroscopic emission of gravitons or gravitational waves from that material that is matched to the ambient impedance of free space, then potentially you could leverage this effect to produce an appreciable field. And I think that last point, that we need some sort of gravitational antenna, is perhaps the interpretation that a lot of people that I haven't seen out there, except for only a few papers. So I've only found a couple of examples where people even attempted to simulate a gravitomagnetic field, and it's never, at a smaller scale, it's always like a black hole or something like that. So you can see the example here. But what would a structure look like that could interface with the, we're basically living in a capacitor, if you think about it from the electromagnetic analogy perspective, where the, Earth is like a capacitor. And how do you create a gravitomagnetic oscillation that will interface with that capacitor to cancel off the fields that you're subject to? So that's kind of the essence of the theory. One of the big questions is does the order of magnitude kind of math check out? So you could look at the gravitomagnetic field at the center of a spinning disk, a macroscopic spinning disk. Let's say a 1 kilogram mass, is orbiting at a 0.1 millimeter radius at 1 megahertz, so ridiculously fast speed. The gravitomagnetic field you could create is 10 to the minus 18th, so like tiny, very, nothing you could do with that. And then you need to be able to change that angular momentum with time. And so obviously you've got G's that your material is going to experience, and so that's just not really a viable idea. The macroscopic angular momentum of a spinning disk is just not enough. But if we assume, as the big assumption here, that quantum spin and classical angular momentum are equivalent, then okay, maybe we're onto something. So let's think about bismuth 209. And I don't pick bismuth 209 out of the blue. I've done a lot of reading in the UFO lore, and bismuth seems to come up a lot. I'm not sure if there's anything really there, but it seems like a great candidate for this theory because it has a very high ground state spin. And so you could think of a 1 kilogram mass has an intrinsic angular momentum on the order of 10 to the minus 10th joule seconds. You could calculate its moment of inertia. You could think about each atom having some radius spinning around some center axis. And then you could figure out what that orbital frequency is, which is ridiculously high. So you could think of, hey, each atom actually has an associated gravitomagnetic field associated with it. So if you had every atom within a 1 kilogram material aligned, you would have actually a reasonable sized gravitomagnetic field. And if you could change that with time, that suggests that you could create a gravito-electric, aka gravitational field. And over here we've got the cartoon illustration of bismuth 209 sort of wobbling around some center axis, and this idea that you could use quantum angular momentum to affect the gravitational field is not new. This isn't something I came up with on my own. This is, a lot of people have suggested a link between superconductivity and gravitation. I think one of the most prominent in there is Ning Li. Douglas Torr had a series of experiments papers back in the 90s. I took this quote directly out of that because it's really the essence of the theory. Coherent alignment of lattice ions spins will generate a detectable gravitomagnetic field, and in the presence of a time-dependent applied magnetic vector potential, a detectable gravito-electric field. And they've got this really big derivation that basically says, when you align all of the angular momentum vectors of these lattice ions, or you can think of the nuclei, nucleons of a material have the same alignment of angular momentum vectors. You could think of it as changing the gravitomagnetic permeability of that material. Whereas, when you have a magnetic material, you've got alignment of electron spin. A magnetic material has all these electrons that are oriented in the same direction with their spin. But a gravitomagnetic material has all of the nucleons with their alignment of spin. And so, this derivation is not without criticism. There are a lot of assumptions that go into it. This paper, is one criticism. I wouldn't claim to really have the mathematics or physics background to stand on either one of these, but it seems like this might be an area worth further investigation. At the same time, Lee had an experiment in 1997 that was inconclusive, and so that didn't really lend much credence to the theory. But then I know the story goes on. Lee was given some grant from, I think, DARPA, and kind of went dark, and so we don't really know what happened to her research. We don't really know if there was actually anything there. You could go on and talk about the Podkletnov experiments, which is a bit of a rabbit hole, so I'm not going to really dive into that. But basically spinning superconductors, emitting gravitational fields, or causing a gravitational anomaly. I actually had a professor in college that tried to replicate that experiment like many years ago when Podkletnov first introduced this idea. and he was not very keen on, he was actually the same professor that helped me with the EM drive, and he was not very keen on Podkletnov because of his reluctance to help them replicate the actual aspects of the superconducting disk. I guess Podkletnov was a little bit shaky on some of those details, but that's just word of mouth. I don't really know. And then you've got Martin Tajmar, who's done a lot of great work in this field. Did I think gravitomagnetic detection of a London moment or something to that effect, basically induced acceleration fields on the order of micrograms that were correlated with the angular acceleration of a superconductor. You've got the niobium-Cooper pair mass anomaly from Tate, which is another interesting, like very thin film superconductor measuring the mass of of what they would expect the niobium-Cooper pairs to be versus what they measured, and there was quite a large deviation there. And then you've got other sort of maybe related papers, enhanced induction into distant coils, things that seem like they might be related, but I'm not actually sure. So basically what I'm trying to say here is that the idea that I'm presenting here isn't new, but it seems like we're missing something. It seems like there's, we're missing the replication, and perhaps that's because the way that we're thinking about it is incomplete. And I think my sort of thesis here is maybe that thing that we're missing is kind of the impedance matching to free space. We need to think of this as a gravitomagnetic antenna that is emitting a field that needs to interact with the field around it. I can imagine designing a very poor antenna and exciting electrons in the right way, but actually reflecting all of that electromagnetic energy back to source because I didn't design it correctly to impedance match to free space. And so you could probably do the same thing with a gravitational antenna. And so that's kind of what we're getting at here. I tossed this slide in here. I think properties as type 2 superconductors. This is kind of what I think is the best avenue, the best avenue to actually engineer this effect. So if you wanted to align the angular momentum of all these lattice ions, as Ningley says, you probably need to look at superconductors because you can achieve coherent phase of all of the atoms in a material. You can also drive what they call Abrikosov vortices, which is like little supercurrents that are spinning around in circles. And, these supercurrents can be on the order of tens of they can be on the order of tens of atoms in diameter to, 50 atoms in diameter. And so perhaps you could imagine stimulating a pretty large percentage of the atoms using this supercurrent, basically driving that angular momentum up and down. And so there are some papers that suggest the Meissner effect requires this linear combination of magnetic and gravitomagnetic potential to vanish. There are other papers that suggest a transient gravitational fluctuation should be detectable, which kind of derives this from Ginzburg-Landau equations and a lot of fancy math. Basically, this slide is trying to say, hey, this coherence of lattice ion angular momentum could increase your gravitomagnetic permeability. Perhaps we need to look at superconductors in this kind of vortex regime. And perhaps those superconducting materials in the vortex regime need to be made of atoms and or isotopes that have the kind of spin characteristics that, a large ground state spin that can be enhanced, that can be throttled up and down. So recently, and I actually discovered this while I was preparing this presentation for this talk here, is Tajmar published a paper last year that anomalous force measurements from a Cooper pair, which was a null result, unfortunately. He basically put a supercurrent through a high temperature superconductor within a cryostat in a vacuum chamber. He's got a setup that can measure on the order of 100 nanonewtons. So that is the best resolution I've ever seen for a thrust stand. And it seems very well characterized and very well put together. He's got an onboard battery system. He's got the ability to apply decently high magnetic fields. Unfortunately, he did not observe a thrust with his experiment, but maybe there are some reasons that it didn't work. I mean, he had a DC electronic stimulation. He didn't have a time rate of change of the nuclear spin. He's just pushing current through. He's got potentially a lack of gravitomagnetic impedance matching to the surroundings. He's got a large thickness of superconductor, which, I've seen a lot of places. The Tate-Cooper pair mass anomaly had a very thin superconductor on the order of microns. We've also got other observations or other papers that talk about the thickness being very important to seeing this effect. So this paper specifically says that if you generalize the Ginzburg-Landau equations with the gravito-electric and gravito-magnetic components, and you look at the situation where you're close to the second critical magnetic field, so you're in that vortex regime, and you've got a maximum coherence length, you can run the math. This is a paper study, and you can say, hey, well, we could potentially predict a transient fluctuation in gravitational field. And so basically the conclusion of this paper is that you would want to minimize the thickness of your superconductor to find a larger effect, but for a shorter time. And so then you would imagine that you would need to oscillate this effect or pulse or continue to stimulate so that you could see the effects at steady state. Or maybe you design your setup so that you can detect that very quick pulse. So all of this to say, and then we've also got this metamaterial of extraterrestrial origin, which I find kind of interesting because, we've got this, what's claimed to be an atomically engineered material from To the Stars Academy, Tom DeLonge and many others, which is pretty interesting. We've got micron thick alternating layers of bismuth and magnesium. So there's bismuth again. We've got magnesium positive ions that are enhanced 60 times more than typical. An article from Linda Howe. I didn't find like any kind of study article or I don't know, scientific paper backing that claim up. So that'd be cool to see data from that. Same as the next one, material acts as a waveguide at terahertz frequencies. That was from To the Stars Academy website. They kind of just threw that in there and didn't have any kind of source. And I thought, hey, that's kind of like a big deal. If you can make a waveguide out of magnesium zinc, that's worth, publishing. As me coming from the microwave engineering side, looking at, electron cyclotron resonance, waveguides, high frequency waveguides for fusion. I know waveguides pretty well, and I couldn't find anything related to magnesium zinc waveguides at terahertz frequencies. That would be pretty cool. You can imagine that maybe, so I put together a little simple COMSOL model just to illustrate a terahertz waveguide, and it's on the right order of magnitude when it's air-filled. So you can imagine if your magnesium zinc was somehow a dielectric, which I'm not sure how that works, but if that had a high dielectric constant, then those dimensions would shrink, and you'd be on the order of tens, hundreds of microns. And I guess this is maybe, if this is related to a warp drive at all, this material, this claim, then maybe the size scale of the atomic vortical oscillations is an important aspect of it. I'm not sure, but I found this kind of interesting, possibly related, possibly not. So I'm not sure how things got highlighted. That wasn't intended to all be highlighted, but anyway. So I think the proposed next steps, I think Dr. Tajmar has like a state-of-the-art test apparatus and just needs a better test article. He's got the nanonewton resolution thrust stand. He's got the ability to put cryogenics, bring your superconductor down to cryogenic temperatures. He's got the ability to apply high magnetic field strengths. All of the ingredients that you would need to actually test this effect, we really just need to design the right test article. So maybe that requires proper selection of the superconducting material, considering the elemental and isotopic composition. Looking at that ground state nuclear spin, thinking about the microscopic lattice structure alignment. So if you've got, grain boundaries in your material and some of your material is oriented this way and some is that way, it's likely not going to be a good emitter of gravitational waves. Test article excitation, magnetic stimulation. So, what kind of magnetic stimulation, what time rate of change do you need in the RF excitation? Do you, what regime of the type 2 superconductor do you want? Do you want actually that transition region right between type 1 and type 2 superconducting phases? And there's probably something to be said about the penetration depth and also the thickness of your material. So as you know, the Meissner effect, magnetic fields within the material, within the superconducting bulk will cancel out and you have some penetration depth. So that's probably something to keep in mind. And then there's the test article macroscopic characteristics. So, you need to design a gravitational antenna, some sort of radiation pattern, something that's going to couple outside of the body itself. And so, I've been able to get gravitational acceleration of a moon-Earth system in COMSOL, using like the partial differential equation solver. I haven't figured out how to do the gravitomagnetic side of things, and that's kind of been on my to-do list for a while. I haven't figured it out yet, but being a COMSOL guy, it's a fun little side project for me, so I think I'll get there eventually. But for now, that is my talk. Thank you.